Welcome back to another exciting chemistry lesson. In this lesson, we are going to look at how to calculate for average atomic mass from the relative abundance and the mass of isotopes of that specific element. And then we are going to look at how to calculate for the relative abundance of the isotopes in a sample as well. So remember, we have this equation right here. Average atomic mass is equal to the relative abundance of isotopes and its mass, and we continue to add to the rest of other isotopes as well until we are done with it. So let's go and do this one problem. In this problem, we have a mass spectrometry analysis of neon gas. Show that it consists of 91.8% of neon-20 with a mass of 19.9 AMU. And then we have 0.5% of neon-21 with a mass of 20.9 AMU. And lastly, for neon-22, we have 7.7% with a mass of 21.9 AMU. What is the average atomic mass of the element neon? So let's plug in the formula, but before we do that, we have to convert our relative abundance to decimals. To convert percent to decimal, we divide by 100 and move decimal place to the left 2 times. So 1, 2. And here we have 1, 2. And here we have 1, 2. There you go. Now let's plug in our formula. And if you notice, I just plug in the formula. Okay, here's the relative abundance times its mass, and I continue to do it to the rest of the other isotopes as well. And the next step is just plug everything in the calculator to calculate our answer. And it turned out to be 20.06 AMU. And AMU again is atomic mass unit, and this is the average atomic mass for neon. Now let's go down to part B. Calculate the number of neon-22 atoms in a 10-gram sample of naturally occurring neon. So as always, if we want to look at atoms or any type of representative particles, we have to get mole. And the only way to get mole is, of course, we need grams and the molar mass. Go back to relative abundance, neon-22, that is right there, 7.7%. So before we do anything, we have to convert to mole because we are looking for atoms, okay? The only way we can get to atoms is we had to go through mole first. Remember, mole is the centralized unit. So let's plug in our work, and we have 10 grams of neon. And to get grams of neon, we need to convert to mole is using the molar mass. In this case, right there, we have our average atomic mass of neon, which is 20.06 grams of neon. And that is 1 mole of neon right there. And this is just neon in general. We are going to look at neon specific 22 later. Now once we get mole, now let's convert to what is this atom. So 1 mole of neon is equal to 6.02 times 10 to the 23rd atoms of neon. But here's the trick. Only 7.7% of the sample is neon-22, so we are going to multiply by that relative abundance, okay? But before we do that, we need to convert to decimal first. Always multiply in decimal. So we have 0.077. Now we plug everything on the calculator, multiply everything on top, divide everything on the bottom, okay? You can do this. And then our answers turn out to be 2.31 times 10 to the 22nd atoms of neon. So this is a little twist to our stoichiometry a little bit, right? Or dimensional analysis. Now this is neon of 22, okay? So keep that in mind. This is neon of all the neon isotopes, but here we have the relative abundance that belong to neon-22. And this is the 100% of sample, okay? So that's how we apply relative abundance and sample to calculate the number of atoms of specific isotopes. Now let's go try another problem where we have to solve for the relative abundance. In this case, naturally occurring chlorine consists of chlorine-35 with a mass of 34.9 AMU and chlorine-37 with 36.9 AMU with the average atomic mass of 35.45 AMU. What is the percent composition of chlorine of these 2 isotopes? So right here, supposed to be 2 isotopes, okay? Again, we are going to use the same formula, but we have to understand relative abundance. When we look at relative abundance, okay? That is relative to 100%, but the magic number is pretty much 1. Because 100 is the big number, but 1 we can deal with. So there are only 2 isotopes. If one of them is X, the other one must be 1 minus X. So the concept is this. We are going to use a variable to represent the relative abundance because we don't know what they are yet. But we know for sure if one of them is X or whatever variable we use, the other one must be 1 minus something, right? 1 minus X. So that's how it works because there are only 2 parts. One part is this, the other part must be something else. Now let's go back and plug into our formula. First, we have our average atomic mass, which in this case is 35.45, okay? And then we are going to set, again, the first one is going to be X. We don't know what is X going to be, but we know it's X. And time the mass of this case. In this case, we have 34.9. So it worked either way, okay? So keep that in mind. As long as you're consistent with it. So if this one's X, the other one must be 1 minus X. And I'm going to parenthesis this. And this is multiplied to what? The next isotope mass. In this case, is 36.9. There you go. Isn't that easy? Remember the concept of percentage when we have 2 parts. That's the tricky part. Don't get tricked, okay? If this part is half, the other part must be the other half. There's no way else to go. So now let's plug in our math, and we are going to simplify this, okay? So again, we have 35.45, and we can simplify this to be what? We have 34.9x over there because this just multiplied directly. And then we add, so 1 time, okay? So 36.9, okay? And here we have minus 36.9x. There you go. Basic algebra, isn't it? Now we are going to go back in and simplify. We are going to, now I'm going to change different color. We are going to bring this over here, and we're going to group them together to isolate a variable, okay? Now that we have isolated our variable from the rest of the number, we just have to use basic calculation. And here we have negative 0.145. And over here we have negative 2.0x. And how do we get x? Of course, that's pretty straightforward. And there you go. We have x equal to what? We have x equal to 0.725. And now if that is in percentage, that turned out to be what? 72.5%. But before we go anywhere else, let's solve for the rest of them. So if this x represents what? This x belongs to this specific mass, and this mass is 34.9, so that's chlorine 35. So right here we have 72.5%. What about the other one? The other one must be here, right? So in this case, chlorine 37 must be what? Well, we have 1 minus 0.725. That turned out to be 0.275. There you go. And that, in percentage, multiplied by 100, is 27.5%. There you go. 27.5%. Isn't that easy? Now, again, don't get tricked, okay? So the hardest part probably is set up an equation for x and 1 minus x to represent the relative abundance. So again, whenever we have 2 parts, you can always use very similar equation to represent each part using a variable. Now let's go to part B. Calculate the number of chlorine 37 atoms in a 25-gram sample of naturally occurring chlorine. It's very similar to part B that we just solved before, right? So let's go back to the idea of 25 grams of chlorine atoms, and we are going to multiply that by the average atomic mass, which is given to us right there. So we have 35.45 grams of chlorine, and that is 1 moles of chlorine. And now once we get mole, we can convert to atoms of chlorine. These are all the chlorine atoms, okay? All the different types of isotopes. And now we have 1 moles of chlorine, 6.02 times 10 to the 23rd atoms of chlorine. Now with that information, we can multiply how much percent of this is going to be chlorine 37. So in this case, it's 27.5. But remember to convert to decimal. So 0.275. Now we can plug everything in the calculator, multiply everything on top, and divide everything on the bottom. And this gives us 1.20 times 10 to the 23rd atoms of what? In this case is chlorine 37, and that's all we have to do. And now let's go check our answer. And notice here I use e to represent time 10 to the power of something, okay? So that way we don't have to type time 10 to the power of something and submit. And there you go. That's all we have to do. Now let's go check the other answer. Here we have the percentage, and then here, look again, I use e to represent time 10 to the power, okay? So that way we don't have to type time 10 to the power of something. That's too wordy. And now we can submit and finish. And that is all we have to do. And as always, if you have any questions, show your work on a piece of paper, take a picture, and put it in a forum, and we will help you from there. And we'll see you next time on another video.